Hello everybody, welcome to the second half of the course. We're starting Unit 3 today with a very short lesson that should be very easy to understand. And if there's anything in this video that confuses you, please refer to section 5.1 of the textbook like it says at the top of this page. So please print this page off and we're going to fill it in together. I've actually already started a little bit here. First we're going to go through two definitions. Now the theme of this work is momentum and impulse. So first you're going to need a definition for momentum. And unfortunately the definition in the textbook isn't really a definition. It's more like taking a formula and writing a sentence out that matches the formula. Their definition of momentum is the product of an object's mass and speed. I always had the same problem. The definitions for momentum always sounded like that, but what is it? So I put underneath here something for you to think about, a little situation. If you have a car that is rolling to a rest, I don't know why you would stand in front of it, but let's pretend you're standing in front of a car rolling to a rest and you're trying to stop it with your arms. Momentum is just this, how difficult it is to stop an object rolling to a rest. A car that's rolling to a rest has no forward force. So if you were to describe how hard it was to stop that very heavy car rolling to a rest, you would probably want to say, well, there's so much force. There's no force. But the weight of the car and the speed of the car creates a new concept that we have all experienced, but we don't really have a name for it yet until today, and that's called momentum. The formula is so easy. It's momentum equals mv. And the symbol for momentum, although it looks like a lowercase p on a keyboard, and you'll find yourself actually writing it as a lowercase p, particularly if you ever have to type your work, it's actually not a p, and it's not even an italicized p. This is a Greek letter, a Greek alphabet letter, and I can't even remember the name of it. But it's not a P. It looks kind of like a squiggly P. Anyway, in terms of units in this formula, or variables, you've seen them all before. M is mass, and as usual, it has to be in standard metric units of kilograms. V is velocity, and it has to be in standard metric units of meters per second. And so the new one here, squiggly looking P, that is momentum. Didn't leave very much room there for that word, but that's momentum. And if you're multiplying mass and speed together, you get this. You get kilogram meter seconds. And there really isn't anything you can do with that. You can't cancel anything. There are no units that are like last names of scientists and you can break the unit down. That's pretty much what you have. So it's kilogram meter seconds. The second term that you get introduced to in this work is impulse, and impulse is very simply, I don't know why I put 3 lines of writing there, it's just a change in momentum. Very easy. However, let's make some rough notes before we write formulas down here, because a change in momentum, and that's why I've got that delta sign in front of the momentum symbol, a change in momentum is not mv. A change in a variable, regardless of what the variable is, it could be x, it could be time, it could be anything. Change in a variable means you have to take a later version of that variable and subtract it from an earlier version of that variable. So a later momentum minus an earlier momentum, and that would give us the change. Well, each one of those momentums has its own mv. So we would be subtracting 2 different MVs, and each of those would have a different speed. So I'm going to call this V2 and V1. That's the formula for impulse, a change in momentum. So that's actually the very first formula I'm going to write over here. MV2 minus MV1. And the usual things down here, where m is mass, this is just a repeat I guess, m is mass in kilograms, and v is velocity in meters per second. Let's go a little bit further on this formula because there's actually two ways that you can write this formula. So over here in the rough notes, there is a common multiple of m there. There aren't two objects when you do momentum questions, at least not in the beginning here. We'd only be talking about one object. You could take that m out as a common factor and say v2 minus v1. And one of the 5 acceleration formulas, if you were to flip to a formula sheet right now and look at it, one of the 5 acceleration formulas looks like this. Acceleration is v2 minus v1 divided by t. So that formula has v2 minus v1 in it, same as this formula here. So if you isolated this acceleration formula for v2 minus v1, we don't usually do that. We usually isolate for a variable, but you could isolate for v2 minus v1 as a package, and you would get at. Well, if we sub that in as a result, we could rewrite this formula as change of momentum, impulse, is m at. So that could be another version of the formula that we could use, but it's usually not written like this because force equals ma. The typical force formula from grade 11, and there's an ma right there in the formula. So we could write the impulse formula as force t, ft. And that's another version of the formula that we'll write in this box here, that a change in momentum and impulse can be calculated by doing force times time. These two formulas are actually the same. They look different, but it's only because of a minor couple of lines of work, and you get one formula looking like the other. But it becomes convenient depending on how things are given. Sometimes things are given as speeds, sometimes things are given as forces and times. It's nice to have two different choices. And to finish filling this in, you know what this is, where F is force, and it has to be in newtons, and T is time, and it has to be in seconds. And one more time. Squiggly looking P is momentum. And actually, now that we're using a different formula here, if you took a force and multiplied by a time, you could also get, like the force would be in newtons and the time would be in seconds, and you'd be multiplying them together. So there are actually two different ways that you can express units on momentum and impulse. You can express it as Newton seconds, or you can express it as kilogram meter seconds. They're both the same. So believe it or not, you're actually going to get questions that are as easy as example number 1 in the beginning. Read that example, pause the video, it's only going to take you 15 seconds, and answer that question, and then continue on. So if you've done that, this is just one object, one situation, and it's just asking for the momentum. So believe it or not, yes, even though it's grade 12, you would have an answer that's this simple. The mass of the rabbit being 2.5 kilograms. The velocity of the rabbit, 2 meters a second, east. And a final answer of 5 kilogram meter seconds, and east. You are going to get questions that easy. And my suggestion is when you do get a question that easy, watch for units that you have to convert instead, because that's usually the way they try and trick you. The second question. Now I wrote right at the top of this question, this is going to be a question that you're going to get wrong next year in university, the first time you do it. And let's see if we can figure out why, because it actually is a very easy question. Pause the video and read this question. It's very, very important. And actually, while you have it paused, do a rough answer for this question. Very rough. And let's see if you get it right. Chances are you're going to make the classic easy error, and I actually want you to make that classic easy error. So maybe you can write it up here in the corner and we'll just cross it out. You can make a study note to yourself. Do that now. Pause the video. Okay, well hopefully you're back. So here's the situation why people mess this up all the time. In this question, you have a hockey puck traveling north. I'm going to say north is forward. You have a hockey puck traveling forward at 5 meters a second. And then it's going to get hit by a slap shot, and it's going to be traveling south or backwards 40 meters a second. Now this right here is what everybody messes up. That's not a change of speed of 35. Your first impression looking at that is, what are you talking about? You subtract the two speeds from one another. 40 minus 5 is 35. So if you took 35 and divided by the mass, you didn't get the right answer for this question, but that's what everybody does. The difference here is, if you're traveling this way at 5 meters a second, you got to go from 5 all the way down to 0, and then go from 0 all the way back up to 40. So you got a change of speed of 5 and a change of speed of 40. That's a 45 meter a second change in speed. If that confuses you, focus on the signs, because this is 5 meters per second north, and sorry, I hope I didn't confuse you by drawing it across the page. Just consider it forward. This is 40 meters a second south, backwards. So think of it like this. The change in speed, V2 minus V1, it's the final speed is backwards, negative 40 meters a second, minus the original speed, which was forwards, positive 5 meters a second. A negative and a positive will make a negative, and this actually gives you a negative 45 meters a second. So what I'm trying to say is, and you did this before, you actually did this even in earlier grades, sometimes you got to consider the directions. You got to make sure directions are in the same direction before you can use them. And 40 meters a second south could also be written as negative 40 meters a second north. We want directions to be the same in questions, and sometimes you have to change the signs to make them that way. If that's confusing, how the signs work out, think of the real life idea here, that you have to go from 5 to 0 and back up to 40, being a change of speed of 45. Because the rest of the question is easy. A change in momentum is mv2 minus mv1, a change in two speeds. I can shorten that by taking mass out as a common multiple, might as well. So the mass in this question is 0.16 kilograms, and the change of speed, which I already did above, is 45 meters a second. And it doesn't matter whether it's negative or positive, that just indicates whether you're gaining or losing momentum. So the numerical value here is the multiplication of these two numbers, not what you might have had as rough notes. You get 7.2 kilogram meter per second. If you look at the significant digits at the top of the question, if you're interested, 40 meters a second is one significant digit, so you would have to report that as 7 kilogram meter seconds. And then part B of this question uses the other formula. It's saying, what's the force applied? And in this question, change of momentum is force times time. So now that you have the answer, you can rearrange this and say force is momentum divided by t. But the momentum being 7.2 kilogram meter seconds, and the time given in the question, 0.002 seconds. And you actually get a massive force. 7.2 divided by 0.002. 3,600 newtons. It seems like a very big value, but any question where you have things stopping suddenly, whether it's a punch to the face or a hockey slap shot or a hammer hitting a nail, there's massive forces in those tiny, tiny changes of distance. And that's what this question has. There's no distance in this solution, but the whole idea that you go from 5 meters a second to 40 in reverse in such a short period of time gives enormous, enormous forces. Okay, so that's it. There's practice questions here that I deleted as many questions as I could from the regular homework, and there were still 1, 2, 3, 4, 5, 6. There were still 6 questions that were different from one another in some way. I want you to do all these questions. You're going to find them all short. None of these questions are long. They're very short calculations, but each one of them has something slightly different than the rest, whether it's a rearrangement or a unit or an idea like this question, where you've got something reversing direction and you want to deal with it. Some of these questions you're going to find ridiculously easy. So take advantage of it over the weekend. Or, well, you should be doing this today, of course, but it is the weekend, so you've got some time here. Take advantage of it. It's the easiest work of the entire year. And then on Monday, things are going to get slightly more difficult, but you're going to be here in class. We're going to put these formulas together into longer situations, but they're still going to make sense. So we'll start with this, practice the general skills for solving these questions, and we'll continue.